Hello, this is Rick Powers for Basic Statistics, and I'm going to record a video for lesson number 13. Hello, this is Rick Powers from Western Technical College for Basic Statistics. Lesson number 13, probability, math operations, independence. This lesson will consider situations in which we multiply or divide probabilities. Once again, we have a couple of definitions to consider. One major idea in statistics is called independence. Unfortunately, that specific word has multiple meanings within statistics, so we have to be really careful about the context in which we use it. Consider a situation where I have two dice, one red and one blue. Now, if I roll an even number on the red die, there's not some weird connection that would influence the value on the blue die. Since the chances of the events are not connected and they don't influence each other, we call this independence. So, as in the previous lesson, if I win by getting an even number on the red one and not a 1 on the blue one, what is my probability of winning? Just multiply the probabilities. 1/2 times 5/6 is 5/12. We can write this as a formula called the multiplication rule for independent events. The probability of A and B is equal to the probability of A times the probability of B. This formula applies in situations where we're using a tree diagram and the number of outcomes is clearly stated. However, this formula does not work in situations where we have a table of observed values with rows and columns. Let's go back to the example where some people are wearing hats, some are wearing jeans, and some are wearing both. Those wearing hats and jeans would be 2. Hats and no jeans is 4. No hat but wearing jeans is 8. And no hat and no jeans is 6. Recall that there are 20 people, so what are the probabilities? The probability of wearing jeans is 10 divided by 20, which is 0.5. The probability of wearing hats is 6 out of 20, which would be 0.3. Note that for the overlap, meaning those with jeans and hat, the probability of wearing jeans and wearing a hat is 2 out of 20, which is 0.10. But this is not the probability of jeans multiplied by the probability of hats. That's equal to 0.5 times 0.3, which is 0.15. Big idea. Multiplying probabilities to find overlap, also called and, also called intersection, can be complicated. From this example, you can see that the mathematics of multiplying the probabilities from each category does not always give us the probability of the intersection of two sets. It works for tree diagrams when we define the events to be independent, but it doesn't always work for tables of categories. In order to clearly define independence in a mathematical way, we introduce the concept of conditional probability. When we use conditional probability, we are limiting the denominator of the probability and figuring our answers with a limited set. Example, what if we looked only at the people wearing hats and asked, what's the probability of wearing jeans for them? This can be worded as the probability of genes given hats. In symbols, P parenthesis J vertical line H, which is 2 out of 6, approximately 0.33. Note, this is not the same as the probability of wearing jeans, which is equal to 0.50. Again, the probability of wearing jeans given hats is about 0.33, but the probability of genes is 0.50. Thus, the people who wear hats are wearing jeans at a lower rate. We call this situation dependence. Big idea. Dependence means that the categories used will affect the probabilities. This idea of dependence is powerful, but it can easily be misused. If we say that people who wear hats are wearing jeans at a lower rate, that observation could just as well be turned around. Jeans wearers also wear fewer hats. And the numbers tell us nothing about why the relationship is there. One example. Is it true that getting a college degree makes it more likely to get higher wages? Or maybe those who would be good workers and are more productive and would get better jobs are also the types of people who make it through college. Maybe a degree is simply a way for employers to find those quality people. Now let's change our example in order to describe independence. As already mentioned, independence is defined as a situation in which one event does not affect the other one. So what would it look like if wearing a hat did not affect the percent of wearing jeans? Consider our example, but now add 10 people with no hats and not wearing jeans. Here are the new numbers. Hat and jeans wearing 2. Wearing a hat but not wearing jeans is 4. No hat but wearing jeans is 8. But now no hat and not wearing jeans is 16. Again, the probability of wearing jeans given hats is 0.33. But now the probability of wearing jeans is 10 out of 30, which is the same. You might be able to tell that the ratios look balanced. That is, the categories do not affect the proportions. So these categories are independent. One other note about conditional probability. It can be figured by using this relationship. The probability of A given B is equal to the number that is in A and B divided by the number which is in B. That is, the probability of A given B is defined to be the number of people in both categories at once, the and section, divided by the number of people in one of the categories. But if we divide top and bottom by the total number of people, we get the probability of A given B is equal to the probability of A and B divided by the probability of B. This creates the general rule of multiplying. The probability of A and B is equal to the probability of B multiplied by the probability of A given B. Independence then can also be shown in symbols. The probability of A given B is just equal to the probability of A. That is, restricting the denominator to a smaller subset does not change the probability. So the multiplication equation for independent categories, as already described, is the probability of A and B is the probability of A times the probability of B. End of lesson 13.